Hello, it's Scott Manley here with episode 4 of my series wherein I answer very difficult questions from my supporters over at Patreon. Nobody has yet asked me my favourite book or things like that, but yes, let's get started. So Helga has said, "Hi Scott, how can it be that Raptor claims 99% efficiency, but then studies such as Fatima Ibrahimi's latest fusion engine claims potentially 10 times more efficient than current engines?" So this comes down to the meaning of the word efficiency. And efficiency is for engines, right? For heat engines, has a very specific definition where if you have like an internal combustion engine, you have a certain amount of chemical energy put in and you get a certain amount of mechanical work out. And that ratio tells you your efficiency. But we misuse efficiency all the time to talk about rocket engines, mostly because efficiency is a word that people understand. And I will frequently say that an engine with higher specific impulse is more efficient than an energy with lower specific impulse. But that's really not strictly the correct word for me to use, but it's very easy for people to understand because higher specific impulse means the exhaust is moving faster. And so for the same mass of propellant, you get more delta V. Now, the Raptor, I don't know where that 99% figure comes from, but obviously they're trying to push the Raptor to make it as efficient as possible, but it is still a chemical engine. It is burning propellant, and that is being expelled out the back, and its exhaust velocity is measured in kilometers per second. Now, this engine, the Fatima Ibrahimi engine, first of all, it's not a fusion engine. I don't know where people get that idea, but it's probably because it says the same thing that powers the sun. What this engine is it's a type of electrical propulsion system. And in that, you take an ionized gas and you either use magnetic fields or electrostatic charges to accelerate these ions, and you can accelerate them to tens of kilometers per second, so they get higher specific impulse and are therefore more efficient. But the downside is it takes a lot of energy to do this, and you can't get that energy from your chemicals. You get it from solar panels, or you could potentially do it from nuclear reactors or stuff. But the point is, these are two totally different systems, and depending upon how you measure it, the word efficiency is perhaps not the most correct word. Maybe it's not the most efficient way to teach this subject. No, it's just an easy shorthand. Specific impulse is very different from what I would use in terms of efficiency when describing engines. Now, Fatima Ibrahimi's engine, by the way, I said it isn't fusion. What it is, it's a magnetic reconnection thruster, and that's where you have, when you have a plasma, magnetic field lines get stuck inside the plasma and they get pulled around as the plasma moves. And you can get into situations where you've got magnetic fields that are pointing in the opposite direction. And when they get close, they'll actually want to reconnect. And when that happens, it releases a lot of energy. And this happens in the sun, right? These loops get twisted around and then you get them contacting, reconnecting, and you get a burst of energy. So that engine that Fatima Ibrahimi has designed uses this phenomenon to blow off little blobs of plasma at very high speeds. Helga also asks, I've spent 4 minutes on this question already. Any chance the line array effect we know from sound engineering can also occur in rocket engines? And line effect is basically just constructive interference where you have an array of speakers. I don't think so. I think what we're really thinking about is very separate phenomena. You could certainly have a line effect with, shock waves and Mach diamonds, but I don't think that you would get any efficiency enhancement. Although, there are, if you think about it, the aerospike actually uses arrays of rocket engines firing together, but I think that's a completely different effect. Okay, enough. I have to get on to the next question. Andrew Waite. Is there a likelihood of space probes to Uranus and Neptune launching in the next decade or so? So yeah, Uranus and Neptune we visited only once by one space probe. It was Voyager, which flew past it and got all sorts of cool stuff. So I don't think there's any chance of them launching in the next decade for the simple reason that if you're going to go there, you're going to want to get a gravity assist from Jupiter, and the next chance to get a gravity assist from Jupiter is about the start of the 2030s. So basically, in the next decade, I guess you could have them right at the very edge. It depends on the exact orientation, alignment of the planets. But I believe there's a few people talking about it. Obviously, to get a mission together in 10 years is going to be hard. But given that the next opportunity after that is another 15 years away, you have to wait for the alignment of Jupiter, it would be a good time to do it. One of the constraints, of course, is that if you're going to send something to Uranus or Neptune, you absolutely are going to need radioisotope thermal electric generators, and that means you need plutonium-238, and that takes a while to manufacture. So if they're going to do that, they would have to be making it, they would have to have some set aside and ready to go. So the only mission I can think of recently is the Trident mission, which was a Discovery finalist, but it never got selected. Yeah, I would be really nice to see, but next 10 years are largely not going to happen because of constraints of orbital mechanics. Graham Chelius asked, was the light sail a success? Did it prove anything we did not already know? It proved that you could deploy a light sail in orbit, and there have been other light sails, but this was a nice small one. So light sail was launched into a relatively high orbit, and it did show that it was able to change its orbit with, consistent with the laws of physics, and they were able to keep the thing oriented and control it. They didn't actually raise the orbit, but they were able to change the eccentricity of the orbit. They were too low down to raise the orbit because the drag from Earth's atmosphere ultimately was dominant over the thrust that they were getting. But if they placed it into a higher orbit, they could probably have been flying it higher. It's just a shame that the light sail has had so many bad luck moments. Catherine asks, wow, another lot of questions here, I'm going to say. I might not answer all of these in great detail. How were the planets beyond Saturn detected? Oh, this is easy. William Herschel discovered Uranus in 1781. He was browsing across the sky and he saw a little disk and he was like, that doesn't look like a star, it looks like a planet. Neptune, on the other hand, that was discovered by the point of a pen by Urbain Le Verrier, who basically the observations of the planet Uranus showed that its orbit wasn't quite right. And so Le Verrier made a prediction that there was another body out there that was perturbing it. And based on that prediction, I can't remember who went looking, but they found it. They found Neptune in 1846. The thing is, though, Neptune is far enough away that most telescopes wouldn't resolve it as a disk. So I believe that many people saw Neptune before it was discovered. And this is the important thing about planets, is you could see them and not necessarily recognize. You might see an asteroid in your telescope and not recognize it as an asteroid. You have to actually figure out there's an orbit, go back night after night and see that it moves. I think Galileo might have actually seen Neptune in the 17th century and just logged it in his catalogue of stars. Okay. Oh, and of course, Pluto was discovered in the 20th century by Clyde Tombaugh. And Kuiper belts and objects, they were discovered even further out, but they're minor planets or dwarf planets, depending which ones you look at. How do we know how far away a star is? We basically use parallax to figure out the near ones, and then we use standard candles to look at further ones. I have other videos on this subject. How do we know what other planets consist of? How do we know anything about their atmosphere? How do we know what's at their core? Wow. Their core is largely a lot of speculation based on knowing the density of the object and observing magnetic fields and things like that. But, we're still not even totally sure of the exact dynamics of the Earth's core, right? The atmospheres, of course, when they interact with the universe, they get hit by light, they get excited, they emit light, which we can look at the spectra of, so we can understand the chemical composition of the atmosphere. We can use remote sensing to see similar characteristic energies in terms of radiation, either from you can use things like neutron spectrometers and gamma rays and X-rays. You can just science the heck out of things from orbit, and it tells you what it's made of. How does navigation by stars work? Well, from on Earth, you look and you figure out how high the star is, and as it reaches the highest point in the sky, that tells you what latitude you're at, right? As for the longitude, you then need to look at timing, and you either need to have a good clock, which doesn't lose time, or you need to very carefully look at Jupiter and its moons and figure out when they're eclipsing, or look at the phase of the moon. It's all very complicated. Why are orbits or other trajectories conic sections? How was that detected? Kepler figured out that orbits were ellipses. Newton, he came up with his law of gravitation and the laws of conservation of momentum and kinetic energy. And when you take those and apply them to a gravity field with an inverse square law, you naturally see trajectories that are conic sections. And so Newton was able to generalize the ellipse to the parabola and the hyperbola. Math, basically. Tell us more on the ATV mission that nearly failed because of thermal blankets that expanded because of misinvented. Nearly failed. Wow, that sounds... I don't actually know. Jules Verne, though. So Jules Verne was the first ATV that was launched. Okay, so that was the first of 5, I think, European space missions to supply the space station. And yeah, I believe, according to this, it had some problem with the thermal jackets. And I imagine that if there weren't venting holes as it rises up into space, the air underneath these blankets will want to expand out. And if there's not enough room, then it could blow the blankets out. And that would be bad because thermal blankets are there to, of course, control the temperature inside the vehicle. It's going to sit in space, and when it's in sunlight, it's going to get baked. And when it's on the night side, it's going to be very cold. And some spacecraft, they can minimize this effect by spinning, right? Doing the barbecue roll. But if you are a cargo vehicle that has to dock to the space station, your orientation is pretty much locked in. You can't spin while the space station isn't. So yeah, thermal control is really important because you're gonna have to spend extra power doing this. But I don't know about that exact incident. Bojan Hrunkas, could you please comment on the single burn orbital insertion seen on SpaceX SAOCOM 1B launch? I always assume that it takes a minimum of 2 burns to achieve orbit. Okay, so I just checked the video, and this is SAOCOM 1B, which was the one that launched from Florida onto a polar orbit, and the target orbit was 600-kilometer orbit. So yeah, basically, you can go straight into orbit if you like. It depends upon the thrust profile of the rocket, but most rockets, yeah, they will put this spacecraft into a parking orbit, and then they might make subsequent burns to adjust this. And I know they do this on Starlink. They will put it into a lower orbit with an apogee that's slightly higher up and make that second burn to circularize it. But yeah, I think if you go into a lower orbit first, then it's marginally more efficient than if you go into a higher 600-kilometer orbit with a single burn. But I don't know exactly how much more efficient it is. Now, if you think about it, SAOCOM 1B, I believe they also did like a return to launch site landing recovery on that. And that would have meant that it was actually slightly advantageous for them to take a slightly steeper trajectory, because that means that when the booster does the flip around, it's closer to home. And that would actually be compatible with them going up into a 600-kilometer orbit. So yeah, look, you can go into orbit with a single burn. You can correctly time your trajectory so you circularize it during that burn. In Kerbal Space Program, I'm going to say, if you played that a lot, then you will notice that it's quite common that you coast to altitude and then circularize that. That's simply because in Kerbal Space Program, the planet is 10 times smaller, but the atmosphere is roughly as thick. So you sort of end up having some coasting in there unless you have some very low thrust stages in between. But in real life, you're accelerating up to 7 kilometers per second. It takes a lot longer to get there, so you can do that in a single continuous burn if you want. So yeah, orbital mechanics, it's you had an option either way. That's all I'm going to say. Matt Townsend, does asteroid mining make sense? Given that modern economics will eventually exploit surface ores to exhaustion, will it be possible for asteroid mining to be viable within near-term technology limits? do we need to do a much better job at husbanding all of our fossil resources on the surface of this planet? So first of all, you're saying fossil resources, don't confuse those with fossil fuels, because you're not really going to get fossil fuels from asteroids. But yeah, minerals. The thing is, ores are just materials where a certain desirable element or chemical or whatever has been concentrated. If you pick up a random piece of rock, it's going to contain a huge mess of all sorts of materials in it. But, things like, I'm trying to think of a fancy name. I can't think of a mineral name, but you go and you look for specific ore. You find uranite, right? Oh, actually, I've got some here, right? I've got some uranium ore in that cup. And that is where uranium has been concentrated into specific places. And so if you're going to mine rock to get minerals, you're going to get the stuff where it's concentrated. Now, in asteroids, a lot of the processes which concentrate minerals on Earth don't apply. There's a whole different set of processes. But on the Earth, you pick the ones where it's very concentrated. And if you have a bunch of different places, you're going to pick the ones with the highest concentration. And eventually, as those get mined out, you'll go to the next one down and the next one down. And eventually, the concentrations might get low enough that there's a better option for something in space. And it's entirely down to this whole thing where cost of space flight will go down, and the cost of mining certain minerals on Earth will go up. And eventually these things might cross, and you might find that it's cheaper to mine certain things in space. And the obvious thing to mine in space are siderophile elements, right? Those are the ones that love iron, and those are the ones that sank to the core of the Earth. Gold, platinum, right? Those, when the surface of the Earth was molten, they dissolved into the iron and they sank to the core of the Earth. So the Earth's crust is depleted in these valuable elements, which have actually great, uses. Asteroids, the same process happened in asteroids, and the minerals were concentrated in the core, but asteroids are small enough that they've been smashed apart, and we find meteoritic iron where there are very high concentrations of these materials, but it's literally just a chunk of material in space. So something like Psyche, which is a big asteroid in the main belt, may have huge amounts of these minerals available in a very small space. And that is just down to a concentration mechanism which creates the material which couldn't happen on Earth. The Earth isn't going to get destroyed, hopefully, to expose the core, but something like an asteroid, that can happen. I'm not saying it's ever going to happen anytime soon, but that's the economics of the situation. Okay, I'm really taking my time over questions. I'm going to have to stop though. Arnold asks, "Hi Scott, the frequency and quality of your content is remarkable considering that this is just your hobby. I started watching your channel with KSP, but now I'm looking forward to every new astronomy rocket science video. Even these ones?" Are there any thoughts or insights you can share for the future development of your channel? I'm going to say, if I don't know how to do this stuff, sometimes wish I had a manager that would just come along and say, "Okay, well we got something for you to do." It's like, great, let's get to work on this thing. I sort of like being a complete amateur at this. There's a certain love of that. It would be nice to make this all shiny and professional, but I simply don't have the time. I mean, that's the difference between me and many of these other high-profile science channels, that I write the stuff in my head. I rarely rehearse any of this. I don't have fancy graphics most of the time, except when the whole video is about fancy graphics. Like when I'm doing 360 videos of wormholes or black holes, that's me just using my math to make cool graphics. But I don't have the time to create fancy animations. And the funny thing is, like, as much as I love music and I've spent years cataloging and picking the perfect pieces of music, I cannot pick music for my own videos. So my point is that I'm happy to remain this sort of weird, scrappy, ugly looking video producer, as long as people are tuning in to watch fun things. I would love to make it a professional thing, but I don't see that happening unless I can somehow cross over some threshold of stickiness that suddenly makes Scott Manley the person to talk to rockets or science or whatever about. Yeah, I don't know. I can tell you what though. In the future development of this video is that I'm going to say I'm Scott Manley. Fly safe.